Welcome back. So when I start to teach anything in lower level algebra, we learn things, and for most kids, they just kind of learn them because they know they're supposed to learn in school. And then there's always a handful of children who vocalize their frustration that they're not sure why they're learning something and what's the point of doing this. So we now that we're getting into upper level mathematics, we get to do a little bit more of that application feature to all of our things that we're learning, especially things that we've already learned the bare bones of. For instance, when we were doing our previous lesson in writing equations of lines given some information. Like, you're not going to go to a job or on the real world and say, oh, this ordered pair is at 2, 3, and this one's at negative 5, 5, and let's find the equation of the line that goes through them because I feel like it. No, you're going to be doing some sort of application, which means we're going to take some real world data or information, and then we're going to kind of translate that to look like algebra. Then we can use our algebraic formulas to go on and actually do something with it. So I'm not going to say all these examples are like amazing and you're going to love them, but you'll be fine. So, this first example here is in 2004, a school population was 1,001. By 2008, the population had grown to 1,697. It's changing linearly, which, sorry to tell you this, it's probably not, but that's okay. For the sake of the problem, let's go with it. How much did the population grow between the year of 2004 and 2008? So we just basically need to do a subtraction problem. So 2004 to 2008, the population went from 1001 to 1697. So a little bit of subtraction, that's 696 is the change. And it went up 696, so it might help you to put a little plus sign there. How long did it take that population to grow from 1001 to 1697? And that was 2004 to 8, so 4 years. So then what they're trying to get you to go towards now is find the average population growth per year. That's fancy talk for rate of change, which is super fancy talk for slope. So they're essentially asking you to find the slope. So the population increased 696 people over 4 years. So if we kind of look at that as a reduced fraction, which I think I did already, that turns out to be 174. So basically every year you gain 174 students per year. And that's, again, assuming it's a linear relationship, but sure, why not? The next question is, what's the population in 2000? There's a couple different ways we could figure this out. We're extending our data kind of backwards. So remember, it was 1,001 back in 2004. And then we have to basically, since we're going backwards now, we got to take away 174 students for every year that we got to go back. So we got to go back to 2003. What are we doing? 2002, 2001, 2000. So we have to subtract off 4 decreases of 174. So I don't know, 305, I think I calculated that to be. So that's fun. That was kind of annoying though. I literally had to hold up my fingers and count how many years. So what if I was tasked with the, job of finding a bunch of different data points? I don't want to sit there with my fingers out trying to count how many years back I got to go. And what if they wanted me to extrapolate like way beyond and into the future? So now would be a smart time for us to write an equation that's going to help us find the population at any given year based on this model. And we're going to say it's years after 2000, which means our model has to start at 2000. So remember, your model is starting in 2000. And we just calculated that there was 305 students, right? So my answer for part E here is that the population can be found by starting with 305 students. And then remember, now we're going forward again. So we're going to increase 174 students every year. So we're going to throw a variable after it, and they said to use t for years. So that's our model right there. And then the last question says, use that equation and predict the population in 2011. So remember, it's measuring years after 2000. So this is when you are 11 years after 2000. So throwing an 11 into your formula here, which is really handy that I already keyed this up, right? No promises that I didn't make a mistake though. Looks like our population is 2,219 students in 2011. So kind of a weird problem because as I'm recording this lesson, it's 2017. So if I really wanted to know the information, I probably would just look up my records. But the problem was probably written a long time ago, but the math is the same. You're still going to find the linear relationship between your data points, and you could either interpolate within the model or extrapolate out. And that's fun. All right. We're going to talk about linear regression in the next unit, and that's really exciting. That's where you have many data points, which is more accurate, right? And the model won't necessarily always be perfectly linear, but close. And then we're going to learn later on in the year about other regression formulas that are, not linear and maybe they're exponential or logarithmic, quadratic regression, all sorts of good stuff. A phone company has a monthly cellular plan where customers pay a flat amount and then a certain amount of money per minute used on the phone. This is very old school. You don't pay for phones this way anymore. So if a customer uses 410 minutes, the cost is $71.50, and if a customer uses 720 minutes, the cost is $118. Find a linear equation for the monthly cost as a function of x, which is the number of minutes used. So they just told us that they want x to be the number of minutes. Ooh, that's ugly. And then we'll say y, it doesn't really matter, to be the total cost. So we're going to have to kind of set up our information that we have as data points. So 410 minutes, cost is $71.50. So right there is an ordered pair of 410, comma, 71.5 is good enough. And then the next ordered pair is 720 minutes, the cost is 118. All right, we got two ordered pairs. Looks familiar, right? I know they're not great, but guess what? The real world, it's not great. So we're going to have to find an equation. We know that if we have 2 points, we can find an equation by first finding slope, and then using our favorite point and using point slope form, and then we'll have an equation that we can manipulate to however we want it to look. It probably would make more sense if we get this all the way to slope intercept form. So first thing we're going to do is find slope. y2 minus y1 over x2 minus x1, and I already calculated this. Turns out to be 0.15. I know normally our slope is a fraction, but remember we're working with money, dollars and cents. The 0.15 probably makes more sense for our information here. If you really wanted to turn this back to a fraction, I guess you could. That's our slope. We're going to talk about what that means in a second, and then we're going to use our favorite point. I don't think I have one. I'm going to go with this one because I don't like decimals. All right, y minus 118 equals, I have to use a decimal, 0.15, x minus 720. And then after a little bit of distribution, and then collecting my like terms, I get 0.15x plus 10. So I already knew the slope was 0.15, but now I can see through my manipulation of the equation that my y-intercept is 10. So the next question says, what does that mean? Like, I can't just run around my job screaming numbers and variables at people, unless you're a math teacher. So they want to know what does this information mean? You got to explain it to everybody else. They're paying you the money, right? So the slope, remember, is rate of change, and we calculated it by figuring out the dollars, the difference in the amount of cost, divided by how many minutes were used. So the 0.15 means that is the cost per minute. So it's 15 cents per minute is how you can interpret the slope. And then the $10, remember, is like if you graph a line, the y-intercept is where it starts. So if you think about that in terms of this problem, it is, remember they talked about there's a flat monthly fee. So it's a $10 flat fee. So your bill is going to start at $10 regardless of whether you actually make any phone calls, and then it's going to increase slowly, 15 cents for every minute that you spend on the phone. It was a struggle back in the day when cell phones didn't used to have these plans you have. All right, use your equation and figure out how much your monthly cost is going to be if you're going to talk for 687 minutes. So into my equation, 0.15, remember x is the number of minutes, so 687 plus my $10 flat fee. And this is money, so if it comes out kind of weird, you got to make sure you round appropriately. I think it comes out to $113.05. So, there's nobody sitting at Verizon or Sprint like hand calculating your cell phone bills. Even now, it's all done through a computer. So it's programmed with a computer. It tracks your minutes, well, not minutes anymore, but your data usage, and it figures it out, and then it bills you automatically. There's no individual person who's whipping out their TI-84 and hand cranking this in the calculator. They have to do a lot of customer bills simultaneously and quickly. So the person who programs the computer to work properly is the person who gets paid a lot of money. That's what we want to be, right? So our next question. Oh, one of my fellow colleagues put this cute little picture in there. It's a moose. Look at that. All right, in 1991, the moose population for a park was 4,360, but by 99, now it's up to 5,880. So cool. If the population continues to change linearly, we're going to find a formula, and then we're going to predict, we're going to extrapolate out of that formula to figure out what the population would be in 2003. Apparently, this problem was written before 2003 because, if I really cared that much, I would just Google it. All right, find the formula for the population P. So these ordered pairs are kind of set up with time and population. So you don't want to actually put the year 1991 into your formula because that's going to make for some really bad math. So if we just pretend that like time starts in 1991, that works for me, right? So at the start of time, which is 0, the population was 4,360. And then by 99, so be careful, 91 to 99 is 8 years later. The population is 5,880. So using those two ordered pairs, I can find slope. Now, the reason I chose to use 91 as my start time is because now I also have the y-intercept, and I can just use the slope and the y-intercept and throw it into the formula. So, yay. Let's talk about our slope. So 5,880 minus 4,360 over 8 minus 0. Got it. All right. So let's see. 190. Looks like our moose are growing by 190 moose per year. And then, like I said, I already have the y-intercept if I just kind of steal that. So the population is 190 moose that are increasing per year. So you have to throw a variable after this. Be like T, sounds good. And then we started with 4,360 moose. And these are measuring years after, remember, 91. So keep that in mind for our next question. Use your model, predict the moose population in 2003. So 2003 would be, little math here, guys, 12 years later. So using our model, throwing a 12 into that formula, looks like I get 6,640 moose. These are things we need to know, right? I mean, I could see a very similar example to this would be, unfortunately, they don't grow linearly, but if you're an environmentalist and you're trying to figure out population of an endangered species, or maybe you're in charge of making sure that the endangered species kind of gets out of that endangered list, and you're going to try to track and extrapolate, like, when will we be off this list? How many years have to go by until we can say, this very rare bird is safe? Like I said, it doesn't really grow linearly, typically, but it's all right. Made for an easy problem for us here at the beginning of PreCalc. Okay, this next one this is a good one. So, Federal Helium Reserve. Yeah, I don't know. I don't know if that's a thing. Held 16 billion cubic feet of helium in 2010, and it's going to be depleted by 2.1 billion cubic feet per year. I'm sorry, I'm laughing. If this is a real thing, I apologize. Okay, give a linear equation for the remaining helium, call it R, in terms of T, and T is going to represent years since 2010. So good news that beginning time of 2010 means I already have my y-intercept when I go to write my equation. Okay. Now leave the billion cubic feet part of it off. So whenever we do the math here and I get like an answer of like 22.1, I'm not going to. We're going to have to remember that represents billion cubic feet. So let's figure out slope. So this first ordered pair, remember, is the start of time is 2010. So 0, we started with 16. Abruzzo, no. They already told me slope. It's being depleted by 2.1 billion cubic feet per year. That's slope. All right, I think I'm done for the first part. The reserve is being depleted, so subtracting 2.1 every year, billion cubic feet, every year, and it started with 16 billion cubic feet. So in 2015, how much is left? So for part B, remember 2015 has been 5 years since the beginning of time for this problem. so T equals 5. So going into my formula, 5.5-ish, I don't know if it's exact or not, billion cubic feet of helium. Man, I really should stop laughing at that because if that's like a thing, I'm going to offend some helium farmers. All right, at the rate of depletion, if it doesn't change, when will the reserve be depleted? So the amount in the reserve would be nothing if it's depleted. So in my formula, the reserve is 0, and we're going to have to do a little bit of algebra here to figure out what that T represents, and then we're going to have to go back and remember what T represents specifically. So if I add the 2.1 T over, and then I do a little division, it doesn't come out beautifully, of course, because, it's life. So it's like 7.6 years. Gosh, I need like a handwriting class. I apologize to my second grade teacher. Remember, T is year since 2010. So 7 to 8 years later would be around 2017. That's now. And 2018. That's later. All right. So again, I don't really know what a helium reserve is, but all right. When hired at a new job, we are given 2 payment options, and this is nice. I wish everyone offered 2 payment options. 17,000 a year plus 12% commission, or you could bump up your base pay to 20,000 and only get 5% commission. So I guess you have to decide how much of a super seller you're going to be. So the question is, you want to actually do some calculation here because we got to think of this. How much do I actually need to sell so that the one option is better than the other option? And then decide if that's reasonable. Man, this is very thought-provoking, right? So the first salary is 17,000 flat pay, but then 12% of your sales. And the other salary is 20,000, oops, plus 5%, careful on the decimal, of those same sales. And the question is, when will one overtake the other? Well, if we just equate them, I think we'll be able to figure that out pretty easily here. So I don't really care how you solve this. I'm going to subtract 17,000, which means at the same time I can also subtract the 0.05x. Now, little heads up, I'm awful with decimals, like really, really, really terrible. So there is no way that I'm going to try to think really hard through this. It's not worth anyone's effort, and I'm surely going to get it wrong. I've just had enough years of getting it wrong to know this. I'm going to divide on my calculator, and I get exactly 42857.14-ish. I don't know if that was exact. I already wrote down the decimal. So that was if I wanted my 2 salary options to equal each other. So this is not an exact science here, guys. We're just going to have a good idea here. It's going to be around or about $42,858-ish and up. So you have to decide, like, are you going to be able to sell that much jewelry? I don't know. I've never sold jewelry before. So maybe talk to some people who already work there and decide how much do they sell every year and is it worth it? So things to think about, right? Oh, fun times. The median home values in Mississippi and Hawaii, and they were adjusted already for inflation, are shown below. So you guys don't really buy houses much here in high school, but if you look at the price that your grandparents or great grandparents purchased their house at, back in the day, and you're going, oh my gosh, I could have afforded a house. No, because you wouldn't have been paid that much money, right? So a dollar was worth something else back in 1950. So they've already adjusted this data for that amount. So don't worry about that. And I'm looking at comparative data for Mississippi. No offense, Mississippi, but I'd rather live in Hawaii. Clearly, I can see from the data that at any given point in history between those years, looks like Hawaii was outranking Mississippi as far as home values. And the trick is we got to figure out which one is growing at a faster rate. I think I can kind of already see that, but let's look. Which state has home values that are increasing at a higher rate? Well, I have a feeling I know the answer, but we should probably compare that, right? So a higher rate is fancy talk for slope. So if I find the, how do I want to notate this? Remember we use M for slope. So let's say the Mississippi slope, sounds weird, was 71400 minus 25,200. So that's the change in dollars over a change in years, which was 2000, excuse me, to 1950. So 50 years. So doing a little calculation there, I got 924. So they went up $924 per year. Then Hawaii slope is 272700 minus 74,400 over those 50 years again. And I already calculated these, comes out to $3,966 per year. So which state is increasing at a higher rate? Clearly, that would be our friend Hawaii. Again, no offense to, Mississippi out there. I'm sure you have a lovely state, but man, why? All right, if these trends were to continue, what would be the median home value in Mississippi in 2010? So they want us to use our data for Mississippi only, okay? They want us to extrapolate out somehow to 2010. So there's a couple ways we can do this. We could just go ahead and set up our linear equation if you'd like, or you could say, all right, so 2000 to 2010, that's 10 more years of gaining $924, right? So if we start off at that 71400 price in 2010 and then bump it up that many more, we're going to get an answer of 80,640. All right. And then if we assume the trend continues linearly, of course, when were they equal? So I love the little note. It might be absurd. Yeah, well, that's what it's gonna be. All right, so we have to write an equation that represents, or at least an expression that represents the home price, median home price for Mississippi and Hawaii. Then we have to equate them like we did with the jewelry store problem. So for Mississippi, if we say time started in 1950, so let's call this like 0. So that's our y-intercept right here. So this is our b. This would be our b. All right. So for Mississippi, home prices start at 25,200, but they increase. Remember, we found Mississippi slope to be 924 per year, and then Hawaii started at 74,400, but increased. I wrote too big. 93966x. And then if we equated them, let's see what happens. It might be absurd. Don't forget. All right, so subtract 924x. I'm going to write over my little graphic there. I'm also going to, oh, this is fun. 4400. We're going to get something negative. Don't panic. We'll talk about what that means. All right, so we get negative 49200 equals 3042x. And then dividing both sides by 3042, I get x equals negative 16.2. What? Think about this. X represented number of years since 1950. So instead of going, forward in time from 1950, I have to take away 16 years. So taking away 16-ish years is about, so around again, 1934. That's when the homes were actually worth the same amount. I wish I knew more about our country state. Sorry to all my elementary teachers. I've failed you big time today. All right, there's your lesson on some linear modeling with data. Again, not very few things in life are going to be modeled linearly, but this is a good start for us. So there's a reason we're learning all this. I